So now I want to wrap up our discussion of active galaxies. Active galaxies really, as I started when I first they gave the first lecture on active galaxies. Active galaxies are really a study of the active galactic nuclei, and we're starting to realize that Seyfert galaxies, radio galaxies, blazars and quasars, they're all powered by the exact same thing, a supermassive black hole that's busy accreting. And so we have kind of a unified model of this. The orientation, you see this makes a difference. If you're looking straight down the jet, you see one thing. If you see at an angle, you see something else. So things that are really far away, then you see radio waves, or you see the light or whatever, and so you get a different sort of view. So this is the unified model of active galaxies. They're all powered by that supermassive black hole. Well, this also indicates possibly an evolutionary path, because quasars and blazars are really far away, and so these are the most distant things that are out there. And so they're the ones that are brightest because they're blazing away so much. And in some sense, that suggests that possibly they are the youngest objects in the universe because they're all so far away. You don't see any quasars or blazars nearby. So maybe the supermassive black hole in a galaxy, once you get a galaxy formed, it eats a lot of stuff at first and accretes a lot of things and blazes it away. Depending on the angle you're looking at it, you see a quasar or a blazar. Or maybe a quasar quiets down a little bit to a blazar, and so this is kind of what we're seeing maybe. And but as they accrete and eat all the easy to eat stuff, they become less active, and then you have something like a Seyfert galaxy, and it's still consuming stuff in that supermassive black hole, but it's not consuming quite as much because you've eaten a lot of stuff. And eventually get to a radio galaxy. Some of the radio galaxies are still accreting, but a lot of what you see with a radio galaxy are those jets that got spewed out while it was busy accreting. And so the radio galaxies might be kind of a later sort of thing. In fact, we see a lot of radio galaxies that are fairly close to us, indicating that they are older in the age of the universe. Remember, the farther away you look, the younger the object is, because the farther back in time you're looking. And then nearby, we don't see any of those things. So very close to us, we only see normal galaxies. They still have supermassive black holes in the middle. The Andromeda Galaxy has a supermassive black hole. Nearby galaxies that we can tell have supermassive black holes. Our own galaxy has a supermassive black hole. But they're not accreting a whole lot at the moment. And so they are much more quiet. There are indications in our galaxy that in the past there's been more activity in the center of our galaxy. So at times we may have been a radio galaxy or a Seyfert galaxy even, but right now we're not. And so again, there's a unified model and a possible evolutionary path between what these objects are. So really, these are all galaxies and different states. So they're all powered by a supermassive black hole that is in fact still present in normal galaxies. The accretion disk, fresh accretion disk, it's fat, a lot of stuff falling into the thing. The orientation of it determines what we see. Sometimes we see a little bit more. For example, almost a billion light years away, or rather, almost a billion parsecs away. So this is like over 3 billion light years away. We saw a flash in the sky, and that was really from some object like a star just suddenly being sucked into the black hole in the center of the galaxy. And so that's kind of a gasp of a dying quasar or a dying blazar or something. Even normal galaxies, like our own Milky Way, has a supermassive black hole in there, and so they're everywhere. Here's a picture of the Andromeda Galaxy, and again, we're pretty sure we got this double core in here, and we can tell by the gas going around that there's still several million solar masses in there, several million solar masses beyond what we see. And again, we can look here and we see that on one side of that core, everything is very, very red shifted. On the other side, everything is very, very blue shifted. And from that, we can calculate it's a supermassive black hole. Now, here's an interesting thing. When we look at supermassive black holes, in most of the galaxies that we measure, the supermassive black hole is between 0.1 and 0.2% of the galaxy's mass. Now, that's for most. There are a few galaxies, the supermassive black hole is way less than the mass of the galaxy, much less than that. There's a few galaxies in which the supermassive black hole is more than that. But this is pretty typical in there. It's so typical that it raises a lot of questions. Why is it so uniform? Why is it always about 0.1 to 0.2% the mass of the galaxy? Well, that strongly suggests there's a relationship between the supermassive black hole in the core of a galaxy and the galaxy itself, the nature of the galaxy. Okay. So this raises like three possibilities. 1, 2, 3. One is the black hole forms first, and it pulls in all the stuff to make the galaxy. And so the black hole might be the first thing that formed, and then when it pulls in stuff, the stuff that gets pulled in is going to be like 500 to 1,000 times the mass of the supermassive black hole. And in that case, then that would explain why the supermassive black hole is 0.1 to 0.2% the mass of the galaxy. Another possibility is that all the stuff is swirling together to make a galaxy. In the middle, it just all clumps up and makes a supermassive black hole. And so as the galaxy is forming up, it turns out the center gets compressed and forms a black hole that's between 0.1 and 0.2% the mass of the galaxy. So between 1/500th and 1/1000th of the mass of the galaxy goes into it. And so that would be another possibility here. And so some astronomers think that the black hole forms first and the galaxy forms around it. Others think the galaxy forms a black hole in the middle. There's a third possibility, and other astronomers think this too, and that is that the galaxy is forming and the black hole is forming, and they form at the same time. So whatever is causing the galaxy to form is also causing the black hole to form. It's not one forms and then forms the other, but rather something is causing them both to form at the same time. And so that's another group that's out there. And we really don't know. We don't really know why yet. And so, among my friends that do, I do stellar astronomy, variable stars, but my friends that do galaxy astronomers, that are galaxy astronomers, I would say that somewhere a little bit less than 40% of them think number one, a little less than 40% think number two, and a little bit more than 20% think something else is actually causing them both to happen. And so I guess maybe 35% think one, 35% think two, and maybe 30% think three or something. I don't know, but we don't really know why. But it is a very interesting idea and something that is still an area of current study.